Hello everyone. So today we will talk about the notion of ordered basis and then the notion of coordinate vector. It's one of the very important topic in linear algebra, and I will tell you its importance maybe in next lecture once I will talk about the linear transformation and the matrices. So today we are going to see these two funda. Okay, so what do you mean by ordered basis? So suppose if you have a vector space V, so V is a vector space you can consider over any field, but let me consider this for simplicity over real numbers. Okay, so V is a vector space over real numbers. So since it's a vector space, it will have some basis. So let be V1, V2 up to Vn. Let me take finite dimensional vector space. So let this B be a basis of your vector space V. Now if I let me call this B1. Now let me call B2 as say V1 bar, V3 bar, V2 bar. So here it was V3 and then V4 bar up to so on. So this is also a subset of V. Now see, as a set, or B1 is same as B2 because I have only interchanged the position of V2 and V3. So this is a basis for V, this is also the basis for V. Your B1 is equal to B2 as a set. But when I say is my B1 so B1 is equal to B2 as a set, yes. Are they equal as a basis set? Yes. But the question is, are they equal as an ordered basis set? Ordered basis set. Now here your answer is no. Because if you observe, we have changed the order. So like here the order was V1 will come first, then V2, then V3 and so on. Here V1 is coming first, but then V3 is coming first and then V2 is coming and then V4. So here we have changed the order. So as an ordered basis, they are not equal. Okay. So be careful when you talk about the ordered basis. If you interchange the position of the vector, you are changing the ordering. And hence as an ordered basis, these two sets are not equal. It's a basis, but as a set, as an ordered set, they are not equal. Okay, and we will see that if you change the order, the coordinate vector also changes. So let's take some example so the concept will become more clear to you. So let's take an example. Suppose you take V equal to R3. We know that R3 is a three-dimensional vector space. And let's take a basis for R3. Let's take the standard basis. What is the standard basis? 1 0 0 0 1 0 0 0 1. This is the basis for R3. Okay. Now let me call this as B1. Let me call B2 as 1 0 0 0 0 1 and 0 1 0. So now here B2 is also a basis, but now I have changed the order. Okay, and let's for practice let me take one more basis, say 1 0 0, say 1 1 0 and 1 1 1. If you are not sure, then you can check that all these three forms the basis for R3. Okay, now let's take a vector in R3. Let's take V bar equal to say 3 7 and 9. We know that this vector belongs to R3. Usually people write in the column form. So if you don't like this way, you can also write in this form. 3 7 9 belongs to R3. Both the notation is okay as you feel like. Okay, so let's use column as a notation. So question is, what you do is you write your vector V bar as a combination of these three basis vector. So let me call this as V1, V2, V3. So what you do is you write your V bar as some linear combination of V1, V2 and V3. And then you write down these coefficients as column wise, C1, C2, C3. Then this column whose entries are nothing but the coefficients of this linear combination, this vector is called as a coordinate vector of V with respect to basis B1. So how will I write? V bar square bracket, and in the suffix I will write B1 because this is the coordinate vector for this basis. Okay, so this is the notation that you usually come across. Okay, so let's try to find the coordinate vector for this vector and b1 ordered basis. So now you know that you can write v bar, which is nothing but 379. You can write this as 3 times 100 plus 7 times 010 plus 9 times 001. Right? You can take these 3 inside. So 300, 070, 009. And when you add, you get the same thing. So here what is the coordinate vector for v with respect to the basis b1? The coordinate vector is 379. Is the same thing. So for the standard basis, the vector is same as the coordinate vector, only for standard basis and in this standard order. Okay. Now let's see what will be the coordinate vector if I take the basis as b2. So for b2, what is this? This is 3 times 100. Now I have 001. So it will be 9 times 001 plus 7 times 010. And now you can see this is 300. You take 9 inside 009. You take 7 inside 070. And what is this? Addition is the same thing, right? So what is the coordinate vector for v with respect to basis b2? It is nothing but 397. So as you can see, as both forms the basis, as a set they are equal, but once I change the order, the coordinate vector changes. So coordinate vector depends on the ordered basis which you choose. So that's why whenever you want to find the coordinate vector, the first step you will see, let b be a fix, let b be the ordered basis. So we always fix the basis first and then we find the coordinate vector. If someone asks you find the coordinate vector, you should ask them that what is the ordered basis, with respect to which ordered basis I should find the coordinate vector. Okay. And if someone has not mentioned, you take the standard basis. That's the usual trend we follow. Okay. Now what about the third one? So I want to write 379 as a combination of 100 plus C2 times 110 plus C3 times 111. Now how will you solve this? If you multiply this inside, this will be C1 plus C2 plus C3. Then you have C2 plus C3 and at the end you have C3. And this is equal to 379. And when you equate both sides, what do you get? You get C3 equal to 9. You get C2 plus C3 equal to 7. But your C3 is 9. This implies your C2 is minus 2. And your C1 plus C2 plus C3 equal to 3. So your C3 is 9. Your C2 is minus 2. So this becomes 7. And therefore your C1 has to be minus 4. So your C1 has to be minus 4 because 7 minus 4 is 3. So therefore the coordinate vector for the vector v with respect to basis b3 is what? What is my C1? Minus 4 minus 2, 9. Okay, so coordinate vector changes as you change the basis, as you change the ordered basis. Now let me take one example for matrices and polynomial and then we will stop. So let's take the second example. So our vector space is nothing but collection of all 2 cross 2 matrices over real numbers and the entries are also real number. So this b1 is the standard basis and this b2 is also basis, but I have just changed the order. Okay, so let's take a vector v bar in this vector space. So let's take say 7, 9, 13 and say 19. Now we know that your v bar can be written as, with respect to b1, it is nothing but 7 times 100 plus 9 times 0100 plus 13 times 0010 plus 19 times 0001. So as I told you earlier, whenever you have a standard basis in the standard order, then the vector and the coordinate vector both are always same. So here also you have 7, 9, 13, 19. So this is nothing but 4 cross 1. Your coordinate vector will always be of the form n cross 1, where this n will be the dimension of the vector space. So here this is a 4-dimensional vector space, therefore 4 cross 1. Previous one, if you observed, R3 was a 3-dimensional vector space, therefore we got 3 cross 1. Okay, now let's go for with respect to B2. So you have first 1 over here. So you will take 9 times 0, 1, 0, 0. Then you have 1 at the last. So 19. So 19 times 0, 0, 0, 1 plus the first entry. 7 times 1, 0, 0, 0 plus 13 times 0, 0, 1, 0. So therefore the coordinate vector for with respect to the basis B2 is 9, 19, 7, 13, which is 4 cross 1. So that's how you find the coordinate vector. And let's go for the polynomials now. So let's take polynomials of degree less equal 3 over real numbers, and the coefficients are also real. Let's take B1 and B2 as the basis for this vector space. Now you take a polynomial, say your P of x is equal to 7x cube plus pi x square plus x plus 3. Now if you observe, let's do first with respect to B1. So you can write our P of x as, it is 1, no? So it is nothing but 3 into 1 plus x and x. So 1 into x plus pi x square plus 7x cube. Right? So 1x x square x cube, 1x x square x cube. So therefore, what is the coordinate vector for this polynomial with respect to basis B1? It is nothing but the coefficient 3, 1, pi 7. And its order is, you can see, 4 cross 1 because this is a 4-dimensional vector space. Now similarly, if you go for B2, so it is x cube is first. So where is x cube? Yeah. So 7 times x cube plus 3 times 1 plus pi times x square plus 1 times x. So what is the coordinate vector with respect to the basis B2? It is nothing but 7, 3, pi 1. So yeah, so that is the notion of coordinate vector with respect to the ordered basis. Now let me give you some homework problems. So these are the 3 homework problems for you. First is 2-dimensional vector space R2. The basis I have given is 1, 0, 1, 1. So write down 4, 3 as a combination of these two and tell me what is the coefficient column wise. V is set of all symmetric matrices of order 2 cross 2. So for symmetric matrices, we know the bases are 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. So write down this as a combination of this. You will get a 3 cross 1 vector. And the last one is this P2. So 1, 1 plus x, 1 plus x square. This is also a basis for P2R, and this is a vector. So write down this as a combination of these 3 vectors. So your job is to tell me the coordinate vector for each of these 3 examples in the comment section. So I hope you understood the notion of coordinate vectors. If yes, do not forget to like, share and subscribe. Thank you.